Welcome to qnawire.
For this problem, on the topic of Gauss's law, we are told that the electric field at one face of a parallelepiped is uniform over the entire face and is directed outwards. At the opposite face, the electric field is also uniform but directed into the face, as shown in our diagram. Now we know the angle at which the two faces are inclined, and we want to calculate, firstly, the net charge contained within the parallelepiped, and we want to know then if the electric field is produced by charges only within the parallelepiped or by charges outside the object as well. So we will find the net flux through the parallelepiped surface and then use that in Gauss's law to find the net charge within. Now we know that for the first surface on the left-hand side, we have the area A equal to 0.06 meters times 0.05 meters, which gives a surface area of 3 times 10 to the minus 3 meters squared. The component of the electric field parallel to the surface, we'll call it E1 parallel, is equal to E1 times the cosine of 60 degrees. And again, these values are given, so this is 2.5 times 10 to the 4 newtons per coulomb times the cosine of 60 degrees, and this gives us the perpendicular component of the electric field to be 1.25 times 10 to the 4 newtons per coulomb. Now we'll do the same for the inward face, and we can then calculate the fluxes. So the area A for the other face is the same, 0.06 times 0.05. So again, this is 3 times 10 to the minus 3 square meters. The component of the electric field perpendicular to the surface, A2 perpendicular, or E2 perpendicular, is the magnitude E2 times the cosine of 60 degrees. And so this is equal to 7 times 10 to the 4 newtons per coulomb times the cosine of 60 degrees, which equates to 3.5 times 10 to the 4 Newton per coulomb. Now that we have both of the electric fields, we can calculate the flux at both surfaces. So the left-hand side has flux, we'll call it phi E1, and this is equal to the perpendicular component of the electric field, E1 perpendicular, times the surface area A. And this is 1.25 times 10 to the 4 newtons per coulomb times the surface area of 3 times 10 to the minus 3 square meters. And calculating this, we get the flux through the first surface, the magnetic flux, to be 37.5 Newton meter squared per coulomb. Now we calculate the flux through surface 2, we'll call this phi E2, and this is again now minus, since the flux inward is negative, that's minus the magnitude of E2 perpendicular to the surface times the surface area A. And so this is minus 3.5 times 10 to the 4 newtons per coulomb multiplied by the surface area of 3 times 10 to the minus 3 square meters, which gives us the inward flux to be minus 105 Newton meter squared per coulomb. So now we have the inward and outward flux, and so we can calculate the net flux. Now the net flux, we'll simply call it phi E. So this is electric flux, not magnetic flux rather. So the electric flux is equal to phi E1 plus phi E2. And this is positive 37.5 minus 105. These are both in SI units, which gives us a net flux of minus 67.5 Newton meter squared per coulomb. Now the net flux is negative, so this means that it's inward. So the net charge enclosed is also negative. Now we'll apply Gauss's law to find the enclosed charge. Now Gauss's law says that the electric flux phi is equal to the enclosed charge over epsilon naught. And so therefore, the value for the enclosed charge which we wish to calculate is equal to the electric flux times epsilon naught. And this is minus 67.5 Newton meter squared per coulomb multiplied by epsilon naught, which is a constant 8.854 times 10 to the minus 12, and that's coulomb squared per Newton meter squared. And so calculating, we get the enclosed charge in the parallelepiped to be minus 5.98 times 10 to the minus 10 coulombs. So that's our first answer. We now know the net charge enclosed in the parallelepiped. Now, secondly, for part B, we want to know if this electric field is produced by charges only within the object or due to charges outside the object as well. And the answer for this is that if there were no charges within the parallelepiped, the net flux would be zero. And this is not the case, so there must be charge inside. Now the electric field lines that pass out through the surface of the parallelepiped must terminate on charges. So therefore there must also be charges on the outside of the parallelepiped.